So far, the integrals that we've seen have been definite integrals, which means they have lower and upper limits, and they mean to find the area under the curve that's given inside the integral between the input values that are the lower and the upper limit. And we found out that we can evaluate a definite integral by finding an antiderivative for the integrand, the function that's inside the integral, and evaluating that at the upper limit minus what we get when we evaluate that at the lower limit. So capital F of B minus capital F of A. So we already have this idea that an integral means, well, you should probably find an antiderivative if you can. And now we're going to expand our knowledge of what an integral means to include this notation too. If you see an integral that has no lower and upper limits, that's called an indefinite integral, and it's just a shorthand way of saying, please find an antiderivative. And since we won't necessarily have an ordered pair on the original function, what we call an initial value, we're going to expect to include a plus c on the end of our answer. So evaluate the integral x squared minus sine x dx. That means find an antiderivative. Find a function whose derivative is x squared minus sine of x. So I'm going to do this part in my head, and I'm going to remember to add plus c on the end. So the antiderivative of x squared, I'm going to increase the exponent by 1 and divide by the new exponent, and I'm going to subtract. So the antiderivative of sine x, what should I take the derivative of if I want to get sine x as the answer? The derivative of cosine would be negative sine, so that tells me that my antiderivative of sine should be negative cosine, so I'll be subtracting negative cosine, so this is plus cosine of x. And if there had been a constant on here originally, I would never know. I have to put this plus c in to take its place. So this is my first indefinite integral. It's really just a shorthand to say find the antiderivative. Notice, you can always check your answer to an indefinite integral problem by taking the derivative of your answer. So I think in blue is my answer. Over here in red, I'm going to take its derivative just to prove that I get that same integrand back. So the derivative of x cubed over 3 is going to be 3 times x squared over 3 plus the derivative of cosine is negative sine of x. The derivative of this c is going to be 0. So 3x squared over 3 makes x squared minus sine x, which is a perfect match for the integrand I started with. This was me checking my answer to tell me that my original answer was totally correct. If you forget the plus c, you will not get full credit. If you forget the plus c, you're leaving out an infinite number of possible correct antiderivatives. There are times when you're going to be able to work around that, but in general, when we were asked to evaluate an indefinite integral, there must be a plus c at the end of your answer. And another important fact, especially as we move into the rest of the big idea for this section, is that we don't have any tools to evaluate integrals that have two variables. So if you see an integral that contains two variables, something either went wrong, and it's supposed to be an integral with one variable, or this is a problem from a calculus class you're going to take later called multivariable calculus. So if you check out these examples here, check out example 2. Can you evaluate what's the integral of 1 over 1 plus x squared dx? You're going to remember, I hope you'll remember, this is a good time to have a reminder, that the antiderivative of 1 over 1 plus x squared is arctangent of x. If you wrote that as tangent with a little negative 1 of x, that's equivalent, that's totally correct, and I promise I'm going to remember my plus c. I could check my answer by taking the derivative. The derivative of arctangent is 1 over 1 plus x squared, and the derivative of c is 0. So this is a correct answer. But if you look at example 3, can I find the antiderivative of 1 over 1 plus x squared with respect to t? Now I have an integral with two different variables. Somebody is messing with you, or somebody made a typo, it's been known to happen, or something has gone wrong while you were trying to write this integral. So this cannot be evaluated. They will never do this to you on the AP test. I might do it to you on my test just to make a point, but really the reason I'm very specific about this is because what we're about to do is going to involve changing variables inside our integral, and if you change them in a way that leaves you with two different variables, something's gone very wrong, and you should feel like you should not integrate. I want you to notice that this feels weird and strange, and you should not try to integrate. All right, here we go with integration by substitution. This is the real, actual topic of this chapter. So far, all we know how to do when it's time to find an antiderivative is to run through the list of all the possible derivatives that we remember taking and look for one that's the answer so we can figure out what the original function should have been. Or we know how to sort of undo the power rule where you add 1 to the exponent and divide by the new exponent. So what we need is sort of a systematic bunch of tools that can help us evaluate, to help us find antiderivatives when it's not just a function we recognize or a polynomial that we can undo with the reverse power rule. So the main tool of a calculus AB student is what is called integration by substitution. So check out this problem. I want the antiderivative of e to the 7x. I really, really wish that was just e to the x. Because I know the antiderivative of e to the x is just e to the x because that's one of the derivatives that I have memorized in my list. So what we do is we do what's called making a substitution. I say that exponent, which is 7x, I really wish it was just one single letter and not some function, not some number multiplied by a letter. So I'm going to make a substitution. I'm going to let u equal 7x. And if I do that, then du dx would be 7. I'm going to do this because what I want to do is change all the x's in my original problem into u's. If I miss one, I'm going to do this thing that I tried to get you to watch out for, which is accidentally leave two different variables in my integral. If that happens, you have to stop and you have to figure it out. You have to make it so that there's only one variable. But that's going to be my game plan, is try to change all those x's into u's and see if I can't get this into something where I can recognize the antiderivative. So you can sort of imagine this. Du and dx are what we call differentials. Imagine multiplying both sides by dx, and du is going to equal 7 dx. Some people like to write that as their first step. I'm showing you in a couple different steps. My recommendation at this point is to try to solve this expression for dx. Try to isolate the dx. Well, that can happen if I divide both sides by 7, and I'm going to get du over 7 equals dx. So here's this is sort of like a tool box that I have. Everywhere I see u in my original problem, everywhere I see 7x, I'm going to replace it with u. Everywhere I see dx, I'm going to replace it with du divided by 7. You ready? I'm going to go back to my original integral. This was the integral of e to the, but everywhere I see 7x, I'm going to replace it with u. That's times. Nobody ever writes the multiplication dot there, but there's a multiplication dot there. And instead of dx, what am I going to write? I'm going to write du divided by 7. Du divided by 7. So that's the same as 1/7 times du. And I remember that rule that says if I have a constant multiple, I can factor it out to the front. This is going to be the same as 1/7 times the integral of e to the u du. Look at that, e to the u du. That's easy. I know what that antiderivative is. What would you take the derivative, what function of u would you take the derivative of to get e to the u as the answer? That's e to the u. So my final answer, 1/7 e to the u, right? Plus some constant. But my original problem had x's in it, so I don't want to leave a u in an x problem, and I just translate my problem back into an x problem. 1/7 e to the, everywhere I see u, I'm going to replace back the 7x plus a constant. And you could double check. If I took the derivative of 1/7 e to the 7x plus a constant, I would get e to the 7x. Final answer.